Okay. Internal noise is the noise which is generated from the internally designed circuits. Okay, and the external noise is the noise which is done by the man-made noise, or it is done by the cosmic noise. Okay, the externally added noise it is. So now the internal noise has been classified into the different types of classifications. Let us see that the source of noise. Okay, a source of noise, it should be the natural source, it should be the man-made source, it should be the fundamental source. The source of noise should be the natural source, and the man-made source and fundamental source. So you have to classify them into one is the short noise. The first one is the short noise. The short noise is noise which is it is produced due to the short effect. So it produced in all the amplifying devices rather than all the active devices. The active devices are, what are the active devices? All the semiconductor devices may call the active devices. So that is the noise, short noise is produced because of the random variation of the arrival of the electrons and holes at the output electrodes of the amplification devices. So due to that random fluctuation of the electrons and holes within the device may called as short noise. That is random fluctuation of the electrons may called as the short noise. So this electron fluctuation is done in all the amplifying devices. So that is known as the short noise or Johnson noise. Short noise or Johnson noise. So it should be the sounds like shown on the lead shots falling on the material sheet. The mean square value of the current equation in the diode is, you suppose I square is equal to 2 into IN square is equal to so IN square is equal to 2 into capital I plus 2 into I naught into Q and B. So that is amperes. So the formula which is given as the short noise is IN square is equal to 2 into capital I plus 2 I naught Q into B. That is capital I is equal to direct current across the junction, that is the anodes. I naught is the saturation current. I naught is saturation current. Q is the charge of the electron, that is 1.6 10 to the power minus 19 coulombs, and B is effect of noise bandwidth, that is H. So this is IN square is equal to 2 into I plus 2 I naught. I is direct current, I naught is the saturation current, Q is the electric charge, and B is the bandwidth of the noise. Okay. For the amplification devices, the short noise is inversely proportional to the transconductance of the device, and directly proportional to the direct current. The inversely proportional transconductors and directly proportional to the direct current. That is the short noise. The one of the classification is short noise. This is the random fluctuation of the atoms. Atoms in the sense electrons and holes. Random fluctuation of the atoms, that is electron holes in the device, called as limited device. So any active device, there should be a random fluctuation of the atoms. The atoms in the sense electron and holes. Okay, so that is the random fluctuation of that is nothing but the short noise. Where the second classification is partition noise. Partition noise. It is generated when the current gets divided between two or more paths. Okay, it is generated when the current gets divided between two or more paths. We call it the partition noise. be generated due to the random fluctuation in the division, in the division. Therefore, the partition noise is higher than the So therefore, the partition noise in a transistor will be higher than the diode. The partition noise is more than in transistor than the diode. Why? Because the diode has two paths. One is anode and the cathode, whereas the transistor has the three paths: collector, emitter, and base. So because of the three paths within the transistor, that's why certainly the partition of the division of the current, we call it the partition noise. No? So more partition in the transistor than the diode. That's why the partition noise more in the transistor than diode. So the third one is flicker noise or low frequency noise. Flicker noise or low frequency noise. So it will be appear at frequencies below a few or low frequency. It will appear in the low frequency. That's why the low frequency noise also flicker noise. So it is some. It is something called as noise. The semiconductor devices flickering is generated due to the carrier density. So the flickering in the carrier density will causes the flicker noise. So in the conductivity of the material, so there will be produce a flickerness voltage drops when a direct current flow through a device. Okay. And the following voltage is drawn as flicker noise. So the flickering of the voltage variations in the low frequency metal is the flicker noise. It is proportional to the square of the direct current flowing in the device. Okay. So that is the flickering. Flickering noise are appear in the low frequency conditions. Very low frequency conditions. The moment of the voltage drops occurrence in the occurrence as the flicker noise. The next one is thermal noise or Janssen noise or white noise. Thermal noise or Janssen noise and white noise. So the free electrons within a conductor are always in the random movement. Okay, the free electron movement in a conductor always a random motion. So this random motion is due to the thermal energy received by the device. So due to the thermal energy, the movement of electrons in the free that is known as thermal noise or Janssen noise. The distribution of these free electrons within a conductor at a given interval of time is not uniform. The distribution of this free electron within a conductor at a given interval of time is not uniform. So the not uniform means, so there is a spikes are occurred depending upon the time varies. So it is possible that the number of electrons may appear at one end of the conductor as maximum. The density of the electrons at the one end of the conductor is maximum, and one end of the conductor is minimum. So the average voltage resulting from this non-uniform distribution. Non-uniform distribution is 0. So the overall average value should be the 0, but the average power is not 0 because of the distribution of the charge carriers or electrons are non-uniform within the surface of the conductor. Say That's why the non-uniform distribution of the electrons is nothing but a thermal noise. So this is due to the thermal conductivity within the device. Okay, that is simply occurred in the conductors. Okay. So in this thermal noise, non-uniform distribution is 0, but the average power is not 0. And this power resultant is 0, but the average power is not 0. And this power distribution from that thermal energy is called a thermal noise. A power appeared in this device Pn is equal to KTB. KTB. Pn is equal to KTB watts. Where K is the Boltzmann constant, that is 1.38 into 10 to the power minus 23 joules per kilo. And B is the bandwidth of the noise spectrum, that is H. And T is temperature of the conductor. Okay. Sometimes it is called as Pn is equal to 4 KTB. The 4 is the constant variable. So the thermal noise or Johnson noise or white noise is the free movement of electrons within the conductor. Okay. So that is the random movement. The movement of the electrons is non-uniform in the conductor. So that is the thermal noise or Johnson noise. So the Pn is equal to 4 KTBR. 4 KTBR. So you can add some more term here. 4 KTBR. Where K is the constant, Boltzmann constant. T is the temperature, absolute temperature. B is the bandwidth, and R is the resistance. R is the resistance. Okay, simply these are the next one is high frequency or transit time noise. So whereas the low frequency occurred in the flicker noise and high frequency occurred in the transit time noise. The time taken by an electron to travel from the emitter to collector of the transistor becomes comparable to period of the which is being amplified when the transit time effect taken place. Okay, due to the transit time effect, the traveling of the electrons from emitter to collector may affected. This effect is observed at very high frequency conditions. So at high frequency conditions, due to the transit time effect, the traveling of electrons from emitter to collector may get affected. Due to the transit time effect, some of the carriers diffuse it back to the emitter. Some of the electrons diffuse it back to the emitter due to the transit time effect. Okay, this gives rise to a input admittance. When the electrons are travel back to the emitter again, so they gives rise to input admittance. So then the conductance component of which increases with frequency. This means currents indirect the input of device by the random fluctuations. So in the output current, so we'll create a random noise at the high frequency. What happens in the high frequency or transit time noise? So due to the transit time effect, some of the electrons are returned back into the emitter again and produce input admittance again. So it gives input admittance due to the back of the back to the emitter, some of the electrons due to the transit time. So this is a noise. This is a noise. So it occurs at high frequency only. It occurs at high frequency only. Okay. Now So now, students, you have to classify the noise. The source of noise is natural source and man-made source and fundamental source. So classification is short noise. This is due to the uh, uh, short effect. It produces the all amplifying devices or all semiconductor devices. So because of the random variation of the arrival of electron and holes at output, we call it the short noise. So that is I naught I n square is equal to 2 into I plus 2 I naught QB, where I n square is diode current, that is I is the direct current, I naught is saturation current. Because of I n square is 2 into I into QB in general, but 2 I naught is where I naught is saturation current. Due to the saturation current, that effect in the overall ion sphere or ion sphere. The Q is electron charge and B is effect of the noise, bandwidth of the noise. This is one of the classification, the short noise. And second one is partition noise. The partition noise is due to the multipath, more number of parts in the generated in the arrival. That is in the transistor, more number of paths than diode. No, and the paths are emitter, base, collector. There, the 3 paths are there. Whereas in the diode, there is 2 paths. So that's why in the 3 paths, division of current is more. The partition noise is more in the diode transistor than diode. And the third one is low frequency noise or flicker noise. So it will be appeared within the charge carriers in a low frequency condition. So because of the flickering of the charge carriers, that is occurred in the low frequency conditions only. And the next one is thermal noise or Johnson noise. So this is due to the conductors material, that is the density of the charge carriers are more in one place and less in another place. So the overall density is 0 when the power is not 0. Then they appear in the power Pn is equal to 4k TBR, where K is the Boltzmann constant, T is the temperature, and B is the bandwidth, and R is the resistance. Okay. The next one is high frequency noise or transit time noise. This is the appear at the electrons are traveling from emitter to collector. They produce some transit time. Because of the transit time, some of the electrons are packed into the emitter. They produce input impedance. That is one of the noise. So this occurred in the high frequency. This is the type of transit time noise. So now noise in communication system. In the communication system, modulator, filter, and demodulator. Okay. So the X of t is given to modulator, then N of t is there. The modulated signal is given to the adder. The noise is added there. After adding of the noise N of t plus S of t, they produce the current way of t. They give it the band pass filter. The band pass filter output is given to the demodulated signal. The demodulated signal of the message signal traveling from the traveling from receiver. So there should be a modulator, modulation, and demodulation. Okay, in the previous class, we see that the noise in the communication system. Okay, so that noise in an SSB system, SSB-SC system, single sideband suppressed carrier system. So the block diagram of SSB-SC system is just like a DSP system. Already you've seen the DSP system, except for the fact that bandwidth of band pass filter of SSB system, SSB-SC series, exactly half of that of the required of the DSP-SC. The DSP-SC is double sideband suppressed carrier, whereas SSB is single sideband suppressed carrier. On the double sideband, single sideband, what is the difference? So 50% the bandwidth is reduced in SSB than the DSP-SC. Okay. Now this is the block diagram. SSB signal is given to adder and noise is added here. These two signals are added and given to band pass filter. The band pass filter output is X of T. The X of T output is given to product modulator. For the product modulator, cos 2 pi of C of T C given as another carrier there. At the receiver, there is carrier used like transform transistor. So now X of T and this product of cos 2 pi of C of T given the V of T signal. The V of T signal is given to low pass filter. Low pass filter output is given to V of T. So now the channel signal to noise ratio is, so SNR for the channel is called average power of the modulated signal by average power of the noise in message bandwidth. That is S square of T by N naught square of T. Now this is the expression of the S of T for an SSB is given by S of T is equal to AC by 2 of T cos 2 pi of C of T plus AC by 2 M cap of T sin 2 pi of C of T. So the average power of the S of T is equal to S of T whole square now. That is average power. So AC M of T by 2 cos 2 pi of C of T whole square naught plus AC M cap of T by 2 sin 2 pi of C of T square bar. That is S of T square is equal to AC square by 4 M of T bar cos square 2 pi of C of T plus AC square by 4 M cap of T sin square 2 pi of C of T. And you can simplify this. AC square T by 4 is there. That is the average power of the signal. That is the average power of the noise is the pass frequency of the noise into bandwidth. That is not into W. That is signal to noise ratio at channel is equal to AC square by T by 4 into NRW. So this is the average power of the that is the SNR ratio. SNR ratio. Now output signal to noise is equal to SNR output to signal noise. That is average power of demodulated message signal by average power of noise signal. That is MD, that is demodulated signal whole square by the demodulated noise whole square. Now this is the expression. The output of band pass filter is X of T is equal to S of T plus N of T. This is S of T the signal and N of T the noise. Here the type of modulation using SSB only. So the center frequency of the bandwidth band pass filter changes to FC minus W by 2. Therefore, noise signal is expressed as N of T is equal to Ni of T cos 2 pi of C of T minus W by 2. So at the frequency, you can substitute FC minus W by 2. FC minus W by 2 minus N of T sin 2 pi FC minus W of T. So the output of product modulator is V of T is equal to X of T into cos 2 pi of C of T. S of T, X of T is equal to S of T plus N of T cos 2 pi of C of T. That is S of T cos 2 pi of C of T plus N of T cos 2 pi of C of T. So after simple multiplication of this. Now this is the signal. V of t is equal to AC by 2 M of t cos 2 pi FC of t plus AC by 2 M cap of t sin 2 pi FC of t into cos 2 pi FC of t plus Ni of t cos 2 pi FC of t FC minus W by t minus naught of t sin 2 pi FC minus W of t cos 2 pi FC of t. Where E of t is equal to, after simplification of all V of t, please look into the mathematical equations are there. So at the end, you have V of t is equal to AC M of t by 2 into cos can be written like this now, the trigonometric identity. 1 plus cos 4 pi FC of t by 2 plus AC M cap of t by 4 sin 4 pi FC of t plus N naught of t by 2 cos 2 pi 2 FC minus W by 2 t plus cos 2 pi W by t. So minus NQ of t by 2 sin 2 pi 2 FC minus W by 2 minus sin 2 pi W by t. Okay. So that V of t is the output of demodulated signal. So when the V of t is equal to AC M of t by 4 plus Ni of t by 2 cos 2 pi W by t plus N naught of t by 2 sin 2 pi sin pi omega t plus AC M of t by 4 cos 4 pi FC of t plus AC M cap of t by 4 sin 4 pi FC of t plus Ni of t by 2 cos 2 pi FC minus W of t minus NQ of t by 2 sin 2 pi V of C minus W of t. So this V of t is pass through low pass filter. This is demodulated signal, that is pass through low pass filter. Low pass filter, high frequency terms are cancelled out, that is attenuated, and only the low frequency terms are allowed. So the output of low pass filter is V of t is equal to AC omega M of t by 4 and Ni of t by 2 cos pi omega t plus NQT by 2 sin pi omega t. That is modulated signal plus noise. That is up to where the modulated signal is AC MT by 4 and noise is called Ni of t by 2 cos pi omega of t plus NQ of t by sin 2 pi of t. So the average power of the modulated signal is called that is can be average of this demodulated. Average of demodulated is called M of t whole square by mod, that the average signal is AC M of t by 4 whole square, that is AC square P by 16. That like averaging of the noise also, NIT by 2 cos pi omega t whole square plus NQ of t by 2 sin pi omega t. That is averaging of demodulated signal and averaging of the noise also. So now that is Ni of t by 4 cos square pi omega 2 plus NQ of t by 4 sin square pi omega t. So that is N naught omega by 4. Therefore, signal to noise ratio output signal to noise ratio is equal to demodulated signal by the noise signal. That is AC square P by 16 N naught W by 4. That is called AC square P by 4 N naught W. So the figure of merit is given as the figure of merit is called the signal to noise ratio output by signal to noise ratio over channel. Is nothing but the figure of merit. That is AC square P by 4 NRW by AC square 4 NRW. That should be equal. That should be unity. Thus, the figure of merit of the SSB system is unity. So, like in the previous class also, the figure of merit of DSP-SC system also unity. This we compare with these two noise in SSB system, SSB-SC, and noise in DSP-SC. So, both the figure of merit is unity. Okay, students. So with this conclude my topic. The next class will go for some other topics. Okay. next class you can go for today up to you can complete the noise on DS-based system, noise in SSB-SC system. So in the next class you can go for noise in AM system, overall analog modulation, and noise in angular modulation, and noise in frequency modulation. So remaining 3 topics are there in this noise unit. Okay. The next class complete all those 3 concepts. Okay, thank you very much. So students, one more thing is, please go through the material once. So there should be a lot more mathematical equations are there. Okay. So here the unable to express in this PPT as a mathematical equation. Just I can show that the mathematical formula for you. So you have to practice that. Okay. So everything I can provide you and the material. Please go through that and you have to practice. Okay. Thank you. Thank you.